Hello. Today I want to talk about the problem that we didn't get a chance to do in class yesterday. So class problem number 2, just to make sure we're talking about the same thing. So this is the problem that we're talking about, right? So you should have that one from class yesterday. And I want to just walk through it, again, give you another example of how I would think about a problem like this. And really get you to think about the power of just writing out structural fragments, connecting them, and seeing if they work. Because that's something I know a lot of people are asking me about. And I think it's important just to put some ideas down on paper and then evaluate them and see if they make sense based on the spectral data that you have. And it's perfectly fine if you have an answer that isn't the right answer. It'll help you get there. All right, so let's work on this problem. So C5H9BrO2, again, using our degrees of unsaturation rules, we're going to simplify that. We're going to ignore oxygen. Br is the same as H, so it's going to be C5H10. If we do our standard calculation, so CnH2n plus 2, the saturated compound is going to be C5H12. So we have 1 degree of unsaturation. All right, and again, as we've said before, 1 degree of unsaturation and oxygen, I would think carbonyl. Right, and so if we go to the IR, you can see there's a beautiful peak at 1740. And if you go to the structure determination tables that you have, that is a perfect spot for an ester. Right, and I would just quickly verify that by looking at the carbon-13 NMR. If you look at the carbon-13 NMR, there's a perfect ester carbonyl peak at 170. Right, so C13, 170 parts per million. We definitely have an ester. So right now, I'm thinking about that structural fragment. All right, so let's see what else we can get. I would say we're done with the IR. Let's go to the carbon-13 NMR. If we look at the number of peaks we have there, I see 1, 2, 3, 4, 5. All right, so we have no symmetry. All right, and if you look at the positions that we have, right, we have 170, we have 60, 40, 20, and let's say 12, something like that. All right. So here's our carbonyl. All right. These are the ones that are probably alpha to O and Br, and these are alkene. Okay. So nothing too surprising in the carbon-13. So we're going to need to really extract a lot of information out of the proton. Right, so our peak summary for the proton NMR, right, we have 4.4, quartet 1H, 4.3, quartet 2H, 1.8, doublet 3H, 1.3, triplet 3H. And then we have an integration ratio. Well, I told you the H's, so that was actually a bit of a mistake. But let's be clear, if we have an integration ratio, just because I want to make sure we're clear in doing this, 0.15 to 0.30 to 0.45 to 0.45. If you get something like that on the exam, or on another problem like when you're working in lab, again, make sure you divide by the smallest one. Right, and that's going to be 1 to 2 to 3 to 3, right, which is what we have here. All right, so make sure that it's clear how to do that, so when the time comes that you can just do that and it's not a big deal. All right, so this is what we have, and again, when you go to do this, right, very quickly, you're going to say CH, CH2, CH3, CH3, right? And if you add that up, that adds up to 9. We have 9 up there. All right, so we're in very good shape. All right, now we just need to find out where these things are. Again, I hope it's clear that these here are going to be alpha to O and Br. All right, so that tells us that the Br and the O are not attached to the same carbon. All right, O is on one, Br is on the other. We're not sure which one it's on just yet, but hopefully we can figure that out. Let's look at neighbors, right, because we have the splitting information. So quartet, neighbor is going to be a CH3. Quartet, neighbor is going to be a CH3. Doublet, neighbor here is going to be CH. Triplet, here the neighbor is going to be CH2. So I think we've found the pairs that we have here, right? So CH3 to CH2 is going to be there, right? And then we're going to have CH3 and CH there. Okay, and I would say now is a perfect time to start drawing out some structures and see what we can come up with. All right, so we have an ester, so let's start there. All right, so what's next to the oxygen? Well, we can have either the CH or the CH2 next to the oxygen, so let's just draw one of them and see what happens. All right, so let's draw the CH. All right, so we put the CH here, and then the CH3. All right, that would mean on the other side would be CH2 attached to CH. And to fill out the structure, we have to put in the bromine, right? So we put the bromine right there. All right, so that's a pretty reasonable structure to get. Now let's go through and see if it makes sense, right? So let's predict what the spectrum would look like, right? So let's use blue to do predictions. All right, so let's say, let's just work our way through this, right? So this is going to be CH3, CH2, so this is our ethyl group. So this is going to be a 3H triplet, and this is going to be a 2H quartet. All right, there's our 3H triplet, 2H quartet. We're going to have a 3H doublet, and we're going to have a 1H quartet. 1H quartet, 3H doublet. All right, that all looks good, right? Don't forget, though, that we also have to worry about chemical shift, right? And if we think about where this CH2 is going to be, this should be at around 2 parts per million. And then this CH is attached to an O and to a bromine, so this should be, I don't know, somewhere around 6 parts per million. All right, so when we look at those two pieces of information, I think that we struggle to figure out how it's consistent with two peaks that are around 4. All right, so this is a really good structure. It just doesn't fit with those two pieces of information, where the CH is and where the CH2 is. All right, so that's fine. We just need to refine the structure, and that means we can't have the O and the Br attached to the same carbon. So let's refine. So if we refine the structure, again, let's start with the ester. But this time, let's put the ethyl group off the oxygen, right? And then we have the CH and the CH3 over here, and the bromine coming off in that position. All right, so now if we do our predictions, again, we'll use blue to do our predictions. We'll have, again, our 2H quartet, our 3H triplet, the 1H quartet, and the 3H doublet. But now when we look at that carbon, we're going to say that's going to be around 4 parts per million. And, or sorry, that proton. And again, this proton is going to be around 4 parts per million as well. And that agrees much better with the data that we have from the proton spectrum. All right. So again, I think it's really important when we do these problems, just put down a structure and then refine it. Right. There's nothing wrong with that. And I think that's the way that most NMR problems are solved, where you come up with an initial structure, you look at it, figure out it's good but not great, and then you refine and you get to the perfect structure. All right. So anyway, continue to use this strategy, and I hope this will help as you prepare for exam number 1.